Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome. I'm delighted to start this theory day. And our first speaker is Noam Nisan, who will tell us about the borders of Border's theorem.
Okay, so hi. So border with a capital B is actually a person who has a nice theorem called Border's theorem that is very useful in auction theory. And this theorem, the point of this talk is that this theorem cannot be generalized as you would want. And that's why it has borders. So let me start with a very simple problem on marginal probabilities. So what I have here is some probability space that has separated into four regions, maybe according to two random variables, the column random variable and the column one. And what I have here is the probability in each one of these pieces. So conditioned on being in this row and this column, the probability of some event is 0.1. Conditioned on this one, you get 0.5. And what I'm interested really is in the marginal probabilities here. And instead of writing marginal probabilities, I wrote 2 times the marginal probability. So I'm assuming everything is uniform in these 4 things. So the marginal probability of the event, just given that we're in the first row, is 0.3. So I'm writing 0.3 so we can see that it's just the sum of these 2 numbers. And similarly, I have the marginal probabilities relative to the second guy. And the total sum, of course, should probably be the same. The sum of the average of these marginal probabilities should be the total probability of the event, and this should work out both this way and this way, okay? And the question is, what kind of numbers can you have in the blue rows? Can you have any kind of numbers? If I give you a set of numbers in the rows, can you tell me whether it's possible or not? That's the question, okay? So it might seem completely trivial. Surely you should be able to get any number between 0 and 1. But the answer is apparently not. Can you fill in the matrix here so that the average of these two this marginal probability is 0.2, and this marginal probability 1.6, and so on? Is that possible or not? Okay, so that's sort of an interesting natural question. And it's not completely clear. I will prove shortly that it is not. But what kind of numbers can you have there? So in general, if you wish, natural computational problem will be something like that. Suppose you're given, now we have n different random variables, each one taking m different values. And I'm giving you the marginal probabilities for every value of every random variable. Okay, so you get xi of j, the marginal probability of some event that we're thinking about when a certain random variable has a value j. And the question is that possible? Is there any probability space? So I'm assuming that my random variables are uniform. Just for simplicity, you could have the same thing with other probabilities. Is there any way to set up a probability space such that the probability, so what does it mean to set up a probability space? You need for every vector, for every profile of values of the random variables to know what is the probability of the event that we're talking about. Is there any way to set it up so that you get these marginal probabilities? So that's a natural question. It would seem to be very simple. One thing that I should point out that obviously the set of possible values of these marginal probabilities is a polytope, because it's really just a projection of the linear. So if you wish in higher dimensions, the dimension of taking into account all the little xi's here, each one of them is just bounded between 0 and 1. And we're just projecting onto their averages into the, so this is a polytope. And the question is this a polytope you can recognize efficiently? Okay? Seems like a very interesting natural question. So why was I interested in this question on variables? Well, because, so why was I? Because it somehow came up as an auction-like problem. So let me continue to try to say, where am I trying to go? I'm going to try to give you this as from an auction perspective. How do you get this kind of problem from an auction thing? Once we get that, then I can tell you about Border's theorem, which is very nice. So I'm going to tell you what it is, and I'm going to really tell you why it's really so cool, and why lately in the algorithmic mechanism design community, people have really been working it out, and how I would like to generalize it. And then I would fix one way that I would like to generalize, the very simple, more general economic scenario that I would like to be able to get a border-like theorem for. And I will try to describe it. And then I will start playing with this problem and seeing what can I do anything with that problem. And when I start playing with it, it turns out that it's going to be translated into a problem on Boolean functions, and the chow parameters basically on the low Fourier coefficients of a Boolean function. And this reduction will be very simple, apparently. Surprising, but simple. And once we get it that way, then we can actually show it's going to be a sharply hard problem. And that implies that we're not going to be able to actually get a generalization of our theorem because it's too complicated in complexity terms. If you had a nice characterization, it would be like an NP, co-NP, P to the NP, something like that, and you won't be able to do that. And that already gives us our bad result. And then also we'll close the loop and go back to our original problem, saying why the problem that I showed you, whether you can recognize these marginal probabilities, is also sharply hard. So it's a difficult computational problem. Okay? So that's the plan. So
just to understand, you're claiming that there is a polytope such that membership in this polytope is a sharply hard thing?
Yes.
So also understand like the scaling, would it be as hard if every variable only had like 2 values?
Yes, we're going to actually show it when every variable has 2 values.
So basically the problem is you have like a 2 to the n dimensional, you're projecting this 2 to the n dimensional vector of probabilities into the
2n values.
And now you ask if
there is a way to project, yes. The projection of this polytope, of the original polytope, is easy, although it's exponential many variables, and the projection is few variables, but yet it's complicated. Okay, so that's everything is going to be very easy, but I think I hope to spin your head a bit going between model to model. Yes.
So if just another way. So if you're not restricted to have like probabilities which are bounded between 0 and 1.
Then everything's very easy. Yes, that's the whole point. Is it's probabilities are between 0 and 1. That's really the sad thing.
Okay. So let me check.
Okay, so let me cast that. Let's really cast that in an auction. So this is the original example that I had. Here you have a marginal probability of an event, and here you have the probabilities. Here you have the marginal probabilities. I'm going to recast that as an auction thing, where I'm going to treat this number as a probability as an auction between 2 players, where this is the probability that the first player wins. And then the second player wins with probability 0.9. So for this example, we always allocate the item. Okay? So let me just switch that to that situation. So now I have an auction. And the question, so the question is there an auction, if you wish, where the first player wins with probability 0.4 if it has this type value in this situation, and wins with probability 1.4 in this situation. And the second player wins with probability 1.4 if it's in this situation, probability 0.8 if it's in this situation. Okay? So we're assuming that there are 2 players, each one has 2 possible values, and these 2 values are IID. So you get each one of the 4 combinations probability 1/4. Okay? So again, what we have here is, so what I write here is this is the probability the second player wins, this is the probability the first player wins, that's 2 times the marginal probability. In the world of auctions, this is called the interim allocation of this player. Okay? So back to this situation. Okay, so we asked the question, can you fill up the marginal probabilities? Can you fill up the probabilities to get these marginal probabilities? And in the auction setting, can you find what the probability that the first player wins under this type? We're now going to call these types of the players, okay? And the second player wins under this type, and so on. So now we translated the same problem into these question marks. And here is a proof that you cannot do that. So the proof is by coloring the different question marks. And it goes like this. Well, in this case, this player wins with probability 1.6, which means that the sum of the red values has to be 1.6. The sum of the green values has to be 1.6. Now, the sum of the purple value, so now I've already taken a little bit of the question, some of the question marks in these three cells. I didn't touch this cell at all, and this cell has probability exactly 1/4, or in terms of actual numbers, the relative probabilities are 1. So the sum of the purple question marks is 1. And then you see you cannot have, because all the question marks together have to be 4, and even without the black question marks, which are positive numbers, we already are beyond 4. Okay, so that's a proof that you cannot do that. Okay, so generalizing this is exactly Border's theorem. So Border asks the following kind of question, and now let me tell you I'm doing a little cheat here. So for 2 players, my original problem with probability spaces and the auction problem was exactly the same, because anything that the first player didn't take, the second player took. Now when I have more players, more dimensions, then it's different, because in the auction I have a bunch of different parameters. The probability that the first player wins, the second player wins, the third player wins, and that's not exactly the same as the original problem. And originally my thinking was that that's a very tiny complication that we should get rid of, but apparently that's not the case. But I'm now continuing in the auction world. Okay? So Border asks the following problem. You have n vectors, each one of them having n probabilities. These are the interim allocation probabilities, the marginal probabilities. And the question, does there exist an auction with these marginal winning probabilities? Okay, very simple. And in a second, I'll talk about various incentives and things like that. But for now, really, the question is, the content of Border's theorem is just whether the probabilities work out. Okay? And that's the question. Now, Border proved this theorem twice. In 1991, he proved it. And then 16 years later, he wrote another paper saying, oh, by the way, it's just an LP duality. Okay? So this is not, so once you have the correct thing, you can prove it with LP duality. You can even actually cast it as a max flow min cut kind of thing, although it's tricky. And the answer is the following thing. So he says, so the following are actually clearly necessary conditions for this to work. And the necessary conditions are the following. You take some subset of values for the first player, some subset of values for the second player, and so on. These are the things that I'm going to basically color, if you wish. And I'm going to look at the sum of the winning probabilities, assuming that the first player has a value here. Okay? So the first, so big xi of a subset of values is simply the sum of the winning probabilities that he should get. Okay? So I'm going to look at the sum of the probabilities that he should get, each one of the players should get when he has a value in these subset of items. And then I counted part of the question marks, and the question marks I never touched are the ones that are in the complement of all of these sets that I'm now counting. So I'm actually adding the probability in terms of if we're talking about uniform over these values, it's just the size of this subset in terms of probability. And of course, you need all these probabilities to be at most 1 so things will work out. And the interesting theorem is that this is also necessary. This is also sufficient. Let me give an example in a 2-dimensional kind of thing. So you're getting these. Oops, sorry. So you're getting these xi's, capital Xi's here, and capital Xi's here. And the question is that feasible? Can you find an auction in each one of these cells, figuring out the probability that the column player gets the item, the probability that the row player gets the item? Can you fill it up such that you get these marginal probabilities, these interim allocation probabilities? And the point is, here's the necessary condition. Let's look at these 2 rows. It's the probability that the row player has one of these 2 values, and look at the probability that one of the column players has these 2 values. So you need that the sum of these 3 probabilities plus the sum of these 2 probabilities plus all this sum, it better be less than 1. Otherwise, you're certainly not going to be able to do that. Okay? And the statement says that these are the only constraints that you have. That's a very nice characterization of this polytope. Okay? That's Border's theorem. Okay, so now let me just say a few words how to make this completely into an auction kind of thing. So if you're not interested in auctions, you can probably zone out. But okay, so really in an auction you may have, so first of all, I only talked about like a uniform distribution over these possible values of the item.
If I was just caring about probabilities, then there is not much difference here between the case of, say, 1 marginals and, say, 5 marginals. You can think of like an n to the 5, artificially make it like an n to the 5.
No, so it turns out that there is a big difference.
There is a difference?
There is a big difference. So that's exactly, I want to go back to the 1 marginal because that's not my original problem. And I will give a motivation from auction theory for that also, that I want to go back to 1. And it will turn out to make a difference. So for a very long time, I thought it didn't make a difference. And it didn't work out exactly, and I didn't know why. Okay. So basically, now it's not going to be just abstract values. There are going to be actually real values, V1 to Vm, for each one of the values of the players. And these are really the dollar amounts that this is really the value that they get for getting the item. Okay? So now these are actual values and not just placeholders, first row, second row, third row. Okay? And we're going to assume, and so everything here in the auction world that we're talking about in what's called in the Bayesian setting, where you were living with these prior probability distributions on the values of the players, and all the discussion that I'm doing is only an expectation. So we're assuming that all the players are just Bayesian probability maximizers completely, and doing all the calculations this way. Okay, so each player basically knows the distribution of the others, but knows its own value. And and by the way, Border didn't do it only in this finite case that I'm thinking about. It works also for infinite, but if you want to think about computational issues, you'd better make it final, so I'm making everything finite. Border would not be happy, but it's the same, really. And I'm assuming everything is uniform on these values. Again, it doesn't matter. Border theorem extends naturally, nothing new there. Okay, so beyond these values, there's one other interesting thing that an auction needs to specify. How much do you pay when you win? That's another thing that an auction really needs to specify. And it turned out that since we're really talking only in expectation, it's enough to talk about the expected payment that I have if I have certain value. And because all the considerations are in expectation, I can just take that expected value and give it everywhere or something like that. It won't matter. So there is going to be Pij, the expected payment of player I when his value is Vj. So that's something that an auction will need to specify to really become an auction. And then you have two important constraints for whatever you're doing. One of them is called individual rationality, which means the players should not lose. That is, what they pay should be less than what they gain. What is that they gain? Well, with probability xij, they win. That's the probability that they win the item over everything, assuming that they have value Vj. And in that case, they're making Vj dollars. So this is their expected gain, and they better not pay more than that. And the second, which is the incentive one, says that if I have value j, I'd better act like a guy with value j, and I'm not going to gain by misrepresenting my value. And that basically translates to this very simple inequality, saying that if I have value j and I act like a guy j, I'm going to get better utility, which is what I gain from getting the item minus what I pay, than if I act according to some other value j prime. Okay, so for us, none of these is really it's very important, but it's all very linear, simple linear inequalities in the x's and in the p's, in the capital x's, in the marginal probabilities, in the interim allocation probabilities, and in the expected payments. Okay, so why is this border theorem so cool? Basically because it allows us to optimize auctions, to do our calculation of auctions, only using the interim allocation rules, which are only a polynomially many of them, rather than the whole exponential-size matrix of probabilities. Okay? So the kind of things we really are interested in. Okay, so by the way, while Border didn't give a polynomial time algorithm, just gave the characterization, actually it's not trivial, you have to be clever, but you can actually get a polynomial time algorithm for that. And then you really can just use linear programming to do whatever you want, to optimize almost anything that you're interested in the auction space. So suppose that we want to optimize, for some reason, we want to optimize the payment, 0.7 times the payment that the first player gives, and the utility of the second player times 0.9, and maybe the probability that the third player wins, and the revenue of the auctioneer, and the welfare that we get in the system. All of these are just quantities that are very natural in terms of the p's and x's. There are just linear quantities in the p's and x's. And then, since we can now recognize the set of recognize the set of possible interim allocation rules, we just need to do optimization of linear function over a very simple polytope that we have all the constraints, all the constraints. So the constraints are the feasibility ones that Border gives us, plus the incentive constraints and the individual rationality constraints that come from the auction world, which are just linear constraints, and a few of them, and everything's very simple. So you can just run your ellipsoid algorithm, and you're happy, you optimize whatever you want. So that's really cool. So then, okay, so now, but when you look at it from an auction point of view, it's not that there are other things beyond the auction of a single item. There are more complicated things like public projects, there are multi-item auctions, there are lots of things you would like to get the same kind of results for. And for that, you would just need to be able to generalize the border theorem to these other scenarios. You need to specify them in the same way. And you could get the same optimization for anything that you would want to do. And that's been the program that these people have been doing for the last few years. And the situation is as follows. If you really want nice, mathematical, clean, exact extensions of border theorems, very slight generalizations. On the other hand, if you're allowing yourself to be a computer scientist and allow yourself approximation, allow yourself not clean, mathematically nice descriptions of the constraints, but just the computational, efficiently ones, then there are almost completely generalizations work. Okay? So that is the situation, and which is really an amazing result, because now you can optimize anything that you want really for any algorithmic mechanism design problem if you're happy to be a computational approximate guy. So what I wanted to do at the beginning to not be a computational approximate guy, but to be an exact mathematical guy and get the same kind of approximations, but only very little was known. And the question is, can we get exact results, exact optimization result, just generalize the theorem. I mean, like a mathematician would, and get the exact theorem, and which, first of all, would have a nice mathematical structure that maybe we can understand and work with, and not just this completely ununderstandable computational issues, and do it exactly.
Maybe another version of the question, can we learn to love and think that the other things is nice?
Yeah, so computer scientists have learned to love and think that the other things are nice, right? But still, we would like to get something non-approximate if possible. And it seems that for problems that are simpler than the auctions should be able to do that, right? So what our point is that no, this is basically they did what's possible. So now we really should love it, right? Okay, you can't do much better than that. So basically, unless complexity collapses on our head, there is not going to be a nice characterization of the constraints for the border-like polytope, for public projects problem, for multi-item auctions, even with unit demand bidder, for essentially any more complicated problem that we can think of that was not dealt by the tiny extensions that we said, well, cannot be done. Exactly. Okay? And the way we're going to show that, I'm going to show it basically for public projects, and I'm going to show the following interesting art. A public project setting, this is a very simple mechanism design setting, for which, if you want to compute just the optimal revenue, which is definitely one of the many things you could definitely compute exactly if you had a nice border-like theorem, I'm going to show the computing the revenue is sharply hard. Okay? So let me give the problem. Here is the problem. So this government needs to decide whether to build a bridge or not. And the government is nice. It's going to just ask each person in the world, in the country, whether he values the bridge or not. Okay? And it turns out that the people are completely independent in this country, and each one of them can have either two values. Half of the people have no value whatsoever for the government, and half of the people have a value WI, which depends on the nature of the person, and the government exactly knows what this WI is, how much, if I like the bridge, they will know how much I like it according to my demographic, but they don't know whether I like it or not. Okay? And so usually the usual story, this is called a public project, and it's a Boolean public project because there are only two possible values here. And usually the story is that the government wants to make everyone as happy as possible, which in this case is very easy. It definitely builds a bridge because the value is at 0 even for those who don't like it. But our government really wants to maximize revenue. So they're going to ask you how much, whether you want it or not, and they're going to charge you something if you said, yeah, build the bridge. And how much are they going to charge you? As much as possible. So they want to design the best mechanism to actually extract value from players, from all the people in the country, and then get to the decision of building the bridge or not. So they don't care about to build the bridge if people are happy or not, but they just are interested to get the maximum possible revenue. Okay?
They can charge different prices for different people?
They can charge different prices from different people. Okay? And that's the problem. What is the best revenue you can have? Okay, so one thing is, which is a little strange for people who are coming from this field, this is a single parameter problem. Meyerson kills this problem, okay? But there's a tiny little caveat in Meyerson's theorem. It tells you what the optional thing is, so it's very easy to figure out using Meyerson what is the optimal mechanism to get most revenue. The only tiny little difficulty is that the revenue itself is going to be some kind of expectation at that point. And it turned out that computing that expectation is going to be difficult. Now, if we could do the border kite thing of optimizing, we would know also exactly the value of the expectation, and we could do that. So even though Meyerson tells us what is the optimal revenue, what's the optimal mechanism, he's not able to tell us what the optimal revenue is, except by a formula that's not computable efficiently.
So is that parameter needed for the mechanism? Or?
No. It's not.
The mechanism?
It's not. But the point is so the mechanism. So that's interesting. We know what the best mechanism is, and I'm going to tell you in a second. Also, we're going to derive it without Meyerson. We're going to derive it from first principles. So I'm going to tell you what the best mechanism is, but I'm not going to be able to tell you what is its revenue.
But you can approximate by just simulating, running the mechanism.
You can definitely approximate. By the way, so you can approximate everything, as we said, that you can approximate. There are nice.
No, but in this case, the mechanism itself is efficient, so you can
run
it. And
absolutely,
just get,
right, yes. And so that by itself may not be that critical, but the point is what you learn from it is that we were not able to characterize a polytope, because if we could characterize a polytope, what are the feasible interim allocation rules here, then we would also directly be able to actually figure out exactly the revenue, which we can't. Okay, so that's really the point here. Okay, so now I'm going to do the switch and try to figure out from first principles what is the optimal mechanisms here. And it's going to be the following thing. So for every possible, so first of all, let's find indicator variables, xi, which specifies whether my value is wi, the publicly known constant, or it's 0. Okay? So xi is, now I'm going to move to a 0, 1 situation rather than a 0 wi situation, which is good. We're getting closer to Boolean functions. And for every possible profile of values of the citizens, of the bidders, there's going to be a probability that the bridge is going to be built. It doesn't have to be a decision yes or no. It can be some probability, right? We're allowing randomized mechanisms to the designer. Okay, so I'm going to have this Boolean function fi, which of course is a probability, so it unfortunately has to be between 0 and 1. And now let's see what is my revenue going to be. So let's try to think, how much money am I going to take from a player with value 0? How much am I going to take from a player from value wi? So a player with value 0 has 0 value if the bridge is built. So we'd better pay 0. Expected payment should be 0 when his value is 0, because I could give him money, but that's not really going to help me. It's easy to see. Okay? So I definitely cannot take more than 0. Now, suppose that my value is wi. How much money can be taken from me if I'm expected to be truthful? Well, let's see what happens if I say 1 rather than 0. Then I'm going to maybe increase the probability that the bridge is built from the probability of f, given that I said 0, to the probability that f is going to be built, given that I'm going to say 1, where the expectation is over what I don't know what the other players are saying. Okay? So this is the extra probability that I'm winning by lying, okay? And by saying 1 over 0. And in that case, my value from it is wi. Okay? So if I'm charged more than wi times the delta of these probabilities, I'm not going to want to say 1, because I'd rather say 0. I don't want the bridge if you're charging me so much. So the amount of money that I can be charged at the most if I say 1 is exactly this number. Okay? So basically, we've really reduced, so tiny details missing, but this is really the proof. We've completely reduced the revenue maximization problem to the following interesting problem. It's almost a Boolean function. It's like a randomized Boolean function. It's bounded between 0 and 1. we want to find the Boolean function or the pseudo-Boolean function that maximizes the weighted sum with wi weights of the probability of 1 minus the probability of 0. Okay?
Shouldn't it be a Boolean function because it's
It will turn out to be a Boolean function, but it's not clear at this point. Okay, so how can we figure this out? How can we find this thing? Okay, so first of all, let's look at this thing. So now it really looks like a Boolean function. So all the, Parikshit and other Fourier analysis guys will say, oh, this is something we know how to do. And this is how they do it. So if you look at the probability that xi equals 1 minus xi equals 0, it's really, I'm just summing up f of x times either -1 or 1 according to whether x is a positive or is 0 or 1. Okay? So instead of this difference, I'm really having here fx times xi I of x, where xi I is -1 to the power of xi, just turning 0, 1 to -1, 1. Okay? So why is this so useful? And by the way, this thing is really the Fourier coefficient of I, of the singleton I, of this function, also called the Chow parameter. Yes?
Why did you say that you don't know in advance that f is Boolean? Because aren't you just maximizing some linear function?
Looks like a vertex of the polytope, right? You're maximizing a linear function over the...
Yes. Okay.
In the expectation, if you also add the randomness of the algorithm or the mechanism, then it is Boolean.
But you don't need, you don't need to argue that.
You argue that the maximum must be a vertex of the polytope.
Maximum should have no random value.
Yes. Okay. So these are the Fourier coefficient. So really, what are we asking with? We're really asking with the following. So what is a Boolean function or pseudo-Boolean function that maximize the weighted sum of the Chow parameters, okay, of the singleton Fourier coefficients?
So we are trying to find f given wi's and
Yes.
what else? Nothing.
That's it. Nothing.
That's it. Okay.
Nothing. Given wi's, find the f. This is now a mathematical problem because maybe it will be difficult to tell what the f is, but it will not be difficult. So we've taken what we want to optimize. We wrote it now in this Fourier analysis notation, which is so very nice because we can just move the expectation to the outside. And now we take the expectation outside, and in each place, we now need to optimize this thing. But this is very nice to optimize. We can do it term by term, because f has to be between 0 and 1. So how can I maximize this? Well, if this number is negative, I want to take 0. If number is positive, I want to take 1. It's completely obvious, right? So this basically what I'm taking is I'm taking either 0 and 1 according to the sign of this. So the function that maximizes this is really the sign or the 0, 1 sign of your thing, which is really the weighted threshold function. So you look at the sum of the weights of the xi that are 1 and compare them to the sum of the weights of the xi that are 0 and see which one is bigger, and according to that you build or not build. Okay? And that's the best thing. Okay. So, and by the way, Meyerson would also tell you the same thing, surprisingly. Okay. And as you said, this is a Boolean function, which is really nice because it means the best option is deterministic. It's also a monotone Boolean function, which actually means you can make it into not just Bayesian incentive compatible, but also Boolean dominant strategy incentive compatible. So it's all very nice. And now the only problem that we have, okay, so we know what the optimal function is. Can we figure out the sum of the weighted sum of influences, or the weighted sum of things, okay? And it turns out that's very easy to solve. That's sharply hard. That's basically known that playing with Chow parameters, figuring out it's sharply hard. Okay, so our problem is given these w's, and you just want to compute not what the function is. We know what the function is, but just what the weighted sum of these things is. And you can see that, I mean, if you just add yet another bit to it and see when does it play. So suppose I added another I plus first item with a very tiny weight. Then when can it play? It can only come into play if the other guys are exactly balancing out to 0. Okay? And if they're balancing out to 0, that's basically the probability. So his influence, basically his sum of weight, will be the probability that they balance to 0. And you can see that's almost a knapsack problem. So this is sharp knapsack, and you can fill the details. It's very easy. Okay? So that's sharply hard. So let's see what did we get for Boolean functions, and then say go back to what did we get for auctions, and I'll hopefully finish on time. Okay, so we show that it's sharply hard to compute the W-weighted sum of influences. So influences are these biases or these parameters, the difference between the probability with 1 and 0. That these are really the Fourier coefficients of not of just an arbitrary thing, exactly of the W threshold function, because we know that's already the optimal. From this, I want to say, but that also means that you're not able to optimize arbitrary Boolean functions, arbitrary linear functions, over valid Chow parameters. Because if you could do that, you could run the same ellipsoid and get the optimal thing. And so also even recognizing, at least under Turing reductions, recognizing whether you're given a set of possible Fourier coefficients for the first level, realizing whether there is any Boolean or pseudo semi-Boolean function that gives you these is going to be sharply hard. Okay? And the same thing happens with the auction world. Okay? So in the auction world, we already know that the optimal revenue is exactly the answer to this question, which is sharply hard. And in fact, it means that because we can't figure out the revenue for the Boolean public project, you can't characterize, you can't do a border kind of generalization, because if you did a border type generalization where the inequalities of the new polytope were reasonably recognizable, then you would do sharply and reasonable, and that's bad. Okay? And back to marginal probability. So I started with a question of, the problem that I started with was, or this is a slightly special case of the problem, you get inputs P1 to Pn. These are the marginal probabilities of the different n players. And I'm going to assume it's a special case that the total probability is going to be exactly 1/2. So I'm going to call that a balanced thing, that the total probability is 1/2. So the situation for the other one of the two types is going to be exactly 1/2 minus P1. Okay? So this is a special case. So I'm giving these things. And the question, does there exist a probability space with a balanced event, that is, with probability exactly 1/2 of the event, such as that for some other events, which are also IID and balanced, so these are exactly the 2 to the n different possibilities, we have the marginal probabilities given this way. Okay? So that's the problem we started with for the special case of exactly probability 1/2. And now that's really equivalent to the question that we already answered on Boolean functions. Because in Boolean functions, we have the Q's, and the Q's were not the probabilities themselves, but the gap between the probability for 1 and the probability for 0. So that's really translating back and forth is completely trivial, and that's the story. So the original problem is sharply hard. So even though, Boaz, it's only a single-dimensional variant of the border thing, it's harder, even though the border thing is easy. And I'm done. Thank you.
Questions?
So does the positive results sort of match your negative result rules out the exact computation? It seems to allow even like fully polynomial approximations, maybe.
Yes. So yes. So okay. So we do have partial matching. We do have like matching results that you can do it approximately, which anyway is sort of known in the auction world. So it's nothing new so far. We're trying to get it nicer and more general, but basically yes. So what you get from the auction world, you can do approximation extremely well with one FP task.
So you said before that they say 2 marginal, 3 marginal problems are significantly harder. So then, in what sense? So if this is already hard?
No. So okay. So in the auction thing, when you have a different number for each player, basically, then it becomes easy. When you have less than that, when there's a single player number that you get different marginals on the same number, then it becomes hard, apparently.
Yes. Okay, now we have a coffee break until the next talk is at 1:30.